Okay, so we have this project on sound, and just so that we're all on the same page and you know what you should have done, I want to go over it a little bit. So we started with this nice image showing what sound waves look like. Then we drew some of our own sound waves on the next page. We watched the chicken song where these guys played these rubber chickens as if they were musical instruments. And then you probably laughed at me playing this straw kazoo. Then I asked you by yourself on your own time to read this, and I've noticed that some of you are forgetting. When I give you a reading, I generally want you to highlight the important parts of it, and it usually says that I want you to do that. So if you're not highlighting the important text, you're losing points. This is for points. Like on this page, just the highlighting is probably 5 points. So if you don't highlight anything, you're going to get 0 out of 5 right off the bat. So you were supposed to do this on your own, read this half page, answer these questions about it. That should be done. But if it's not, go back and do it. Get those points when you turn it in. Then you probably laughed even more when I played some of my musical instruments for you. You go to this YouTube video and you take notes and answer questions about each of these instruments. This is something else you needed to do by yourself. Largely, I decided to do it as a YouTube because I wanted you to have the freedom to choose when to do it. And I also, it was just easier to set it up in advance. So basically you're looking at these crazy instruments. This one looks like a bow and arrow. And in fact, we think that's where it grew from. The musical bow might have been invented by some hunter, just tapping on his bowstring with his arrow. So we not only looked at these musical instruments, but we applied them to science. These drums from India are the ones that I actually practice with the most. I put hours and hours into working with the tabla. So this part of the project you do on your own time. This will be due next week. Hopefully you're already done with this because you did it and you're staying caught up. So throughout this video, there's 3 things going on. Really, the way I think of this is that it's a little bit about music from different cultures. It's a little bit about the physics of sound, and it's hopefully just kind of fun too. So, musical instruments, cultures, and physics. Then at the end of it, there's a short review quiz. So make sure you do that too. The video would finish here, and then you answer these questions. Again, this has to be all done on your own. All right. Then we had another video that was much more professionally done of the relationship between music and physics of sound, which is called cymatics, where we can visualize what's going on with sound waves. So for example, this guy took this black piece of paper, put it on a speaker that was laying down and playing up towards the ceiling. And then he scattered this white powder on it. And when he plays different notes, the pattern of this powder changes. It's pretty cool to see. And it's kind of a fun song that he's playing as well. So what you're supposed to do is use these vocabulary terms to describe how he is visualizing sound using these different approaches. How can putting light powder on a dark surface show us the sound waves? What about when you put when you put a dish of water on a speaker? Or when you set up a stream of water to come out of a speaker? What happens when you play the notes? What happens when you slow down the video of a cymbal crash? Can you see those vibrations? Can you see the sound waves coming out of it? Use vocabulary. How about flames from a tube? how does that show the zone of compression and the zone of rarefaction when he plays different notes through it? So this was another page you can do on your own at any time. Then that took us to the sound wave simulation. And I think this is going to take us 3 class periods. So the first one we already did, and if you weren't here to do it, or if you didn't finish part of it, I have recorded that class and posted it on YouTube. All you have to do is go look for the link in the team's posts. Just look through the old posts for it, okay? So hopefully you've remembered to label these 2 arrows. Which one is showing the zone of compression? Which one is showing the zone of rarefaction? And let's review what that means. Here's a diagram showing a drum vibrating, which vibrates the air molecules and sends a sound wave through the air molecules to hit your eardrum. Those vibrations are going back and forth. They're not going up and down like waves of water. They're not doing this. They're doing this. And this wave moves through the air at high speed. In some places, the air molecules are squeezed together, and you can see it kind of would make it look dark there. We call that the zone of compression, where they're squeezed, they're compressed. In other places, the air molecules are stretched apart. It would make it kind of light colored, and we call that the zone of rarefaction. The molecules are more rare because they're spread out. So you're supposed to label ZC and ZR on these 2 arrows. One of them shows the zone of compression, the other shows the zone of rarefaction, and it also tells you here which one should be which. The dark areas are where they're squeezed together. So is that compression or rarefaction? The light areas show where they're stretched apart. Is that ZC or is that ZR? And then we just kind of looked at what happens when we played a sound from this speaker and we moved the person closer or farther, which of course changed how loud it was, huh? But when we just mic'd the speaker directly, that didn't change the sound. No matter where the person was, the same note was coming out of the speaker. Next, we talked about amplitude. And the big idea here is that amplitude is the same as volume. So if I increase the amplitude, these waves that we're visualizing became easier to see. They had more contrast. They were more intense. And we could hear that the sound was louder. But if I decreased the amplitude, it got quieter. The volume went down. And the difference between these waves, the dark and the light regions, was much less. After we modified amplitude, we moved on to modify frequency. And frequency is basically the same as the pitch of a note. Whether it's a high note or a low note, that is going to be changing the frequency of vibration, how fast it's vibrating. When you pitch your voice very high, your vocal cords vibrate rapidly. When you pitch your voice low, they vibrate more slowly. That is the same for any sound that you hear, whether it's from a drum, a guitar, a flute, an engine, the wind, a bird. If it's high pitched, it's vibrating faster than if it's low pitched. And we could see that in these waves because when it was high pitched, we could see the speaker moving faster and we could also see the waves coming out faster. But here's the interesting thing. At the same time that those waves are coming out of the speaker faster when we change the pitch, watch what I'm talking about here. And watch the speed of the speaker pulsing. With each pulse, we should see one wave come out of the speaker. Watch what happens when I take it up to a higher frequency. It's pulsing much faster. There's more waves coming out, huh? But look at the size of these waves. Look at the distance between them. Think about that. Keep that in mind and watch what happens when I lower this frequency to the size of the wave. So here we have some high frequency waves still moving past this person and some low frequency waves coming out of the speaker right now. If we were to measure from the center of this black wave to the center of this black one, wouldn't that be a much larger number than from here to here? We call this the wavelength. So what we see is that with a bigger wavelength, we have a smaller frequency. It's only 200. But with a smaller wavelength, we have a bigger frequency. These things are the opposite of one another. And on your project, that's where it asked you about the inverse relationship between frequency and wavelength. Remember, inverse relationship means the opposite of something. When one goes up, the other goes down, in other words. When frequency increases, wavelength decreases. Let's look at that again. Here's our high frequency. So the frequency is a large number here, but the distance between waves is a small number. Wavelength is the distance between these waves. Here it's a small number. Here it's a large number. If we were to measure these with a ruler, we would find this is a much bigger number than between these two waves. So large frequency, small wavelength. They're the opposite of each other. For this big one, large wavelength means small frequency. As one increases, the other decreases. So keep that in mind. We see when we change one, it changes the other also. So we did that together last week. Then we did a lab, the first of 3 labs we're going to do. And what we did was I changed the frequency and we counted 10 waves and measured the time it took for them to go past us. So we were then on this page and we would count 10 waves while this clock was running. All right. And we should have seen this change. You might be able to tell just if I take this way down, how fast are these waves coming out now? If we're going to count 10 of these black bands go past, 10 of these black zones of compression, 10 waves, it's going to take a while, isn't it, when it's a low frequency? But if we crank it up to the highest, look how fast they're coming now. You just count 10 of these and then we stop the clock. Much faster, huh? So we should have seen that relationship, and that's where we finished class last time, and I asked you to do this graph on your own time. So this might be homework. If we ran out of class time, this could become homework. So let's look at this quickly in case you haven't done it, or maybe you want to check yours to make sure it's a good title or that you actually wrote a title for this graph. Now, a good scientific title often is a complete sentence. Usually it's a complete sentence. And it normally includes the important variables that we're studying. So in this experiment, we looked at these 2 variables, the frequency measured in hertz and the time it takes for 10 waves to go by. Both of these phrases, frequency and time for 10 waves, both of those phrases should be part of this title. You want to write a title that helps the reader understand what's going on in the graph. And I think I gave you the hint that a good title often might start with something like this: a comparison between one thing and another thing. Now, guess what you would fill in these blanks? They would be the important variables that we're studying. Or another title might be something like the influence of blank, one of the variables, on blank, the other variable. So you could use these as starting points for writing a good title for this graph. I want to remind you that the x-axis always shows the cause of changes. And this is known as the independent variable, and it's often the thing that we alter ourselves. So that means that our x-axis is going to be frequency down here across the bottom. Don't forget to put a title down there that says what it is. You're going to put numbers on here, of course, and hopefully you start with 0 to show where we started from, and then we just put our frequencies along the way, right? We just keep going up to 1,000. Each line is another 100. But what are these numbers? Are these miles per hour? Is this the time it takes for somebody to, I don't know, to run? No, these are not. These are the frequency of the sound. So you have to include that in a title. Similarly, for the y-axis, you need a title, and that's going to be what we call the dependent variable, which are the results of the change. So our results are down here, aren't they? So this is going to be your title for your y-axis. Now on this one, we also should start with 0. Notice I have to put 0 in there twice because we don't always start the axis at 0. Sometimes it might start at 1,000. So we have to always label whatever that axis is. And I believe, if I'm not wrong, that we were measuring this basically in these amounts, right? Something like that. Does that seem right? Time for 10 waves. And then our maximum, we took this all the way up to 0.1. I think that's what we did, was we basically, if you were to think of these as money, this is 1 cent, 2 cents, 3 cents, on up to a dime at the top. Okay? So you were supposed to finish this graph on your own time and write out your conclusions down here. And that takes us to today. So we're going to do another lab today. And we're going to look at frequency again, but we're going to look at our data in another way. I think I left out the word data here. Sorry about that. We'll gather our data in another way. Should have done a better proofreading job on this, huh? So we're going to gather data in another way. We're going to count the number of waves released during 1/10 of a second, 0.1 seconds. So here's our data table. Once again, I'm going to modify the frequency. And then we're going to count the number of waves that are released in that 1/10 of a second time period. We're going to do each of these rows one at a time as a group. And so I'm going to explain them one at a time. But here's what's going to happen for the lab. Notice it says to fill this one in, the number of waves in 1/10 of a second. One person counts the waves, that's you, while another person starts and stops the clock, that's me. I'm going to run the clock. I'm going to tell you when to start, when to stop counting. Once you've counted how many waves have gone by in that time period, you'll just come back to this page and record your data in here. Now, when we're counting, we might end up with somewhat different results, and that's okay. That's one reason, ideally, we would do this like 5 times, 10 times, 100 times, and take the average. Because one time you might count too many, another time you might not count enough, and the average would balance it out. But we're just going to do this once, and I think that'll be okay. So here's what's going to happen. Here's the speaker pulsing, and I'm going to hit the clock. And you're going to count how many waves are released until I tell you to stop. We're not there yet. You're still counting. Now we're halfway there. Still counting. Keep going until this is 0.1. 0.08, 0.09, and stop. Oh, pretty close. I might not get this exactly because it's measuring it out to the like 10,000th of a second or something. But that's okay. That's good enough for us. All right. So when I tell you to start, and I'll give you a countdown, 3, 2, 1, go, you count and just ignore this clock. Don't even look at it. Instead, you have to stare at one point and count the number of waves that are coming out of the speaker. And we're going to do this at these different frequencies. So we're going to start off, it's going to be a little easier because they're going to be slower. So you have some options of where to do your counting. You could count when the wave hits the edge of this clock. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, like that. And did you see that I was only counting the dark band? In fact, I'm going to make the dark and the light show up as differently as possible by turning up the volume. It also makes the speaker pump a lot more, so you can see that. So one option is to count when the wave hits the edge of this clock, or when the wave hits the ruler up here. Either count the black or the white, not both. Another place that you could choose, if it works for you, you can count in different places. You could watch the wave come out of the speaker. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, like that. Or you could also watch the pumping of the speaker itself, because every time it pumps, it sends out one wave. 1, 2, 3, 4, 5, 6, 7, 8, 9, like that. You just count until I tell you to stop. All right? So we're going to take this down to 100 hertz, our lowest frequency. You need to make a choice of where you're going to count from. And in a moment, I'm going to start the clock and you're going to start counting. Again, you could count when the wave hits the box, the timer. You could count when the wave hits the ruler, either the black or the white, not both. You could count when the wave is released from the speaker, either black or white, not both. You could count when the speaker pumps, either pumping down or pumping up, but not both. All right? So we're going to count the number of cycles that occur in 1/10 of a second. And we're about to begin our first one. So 3, 2, 1, go. Count those waves. We're halfway done. Keep counting. Almost there. Keep going. And stop. Okay. Now go back to the data table and enter how many you counted over here. And I'm just curious to see how we're doing. Will you guys please type in how many waves you counted? Let's see how we did there. Tell me how many waves you got. Okay, thanks, Katsali. All right, Vanessa, good job. All right, look, there's some consistency there. All right, so I see a bunch of you have approximately, well, so far you guys that entered an answer, you all had the same answer, which is fine. You had 10. Some people might have had 9. Some people might have had 11, but you shouldn't have had 20 or 50 or 100. Okay? So that's a fine answer. All right. Let's go back to, oh, and the other thing is, if you need me to redo one of these because you lost count or something happened that you weren't ready when I started it, you'll have a chance to do that in a little bit. If that happens, just skip that one for now, fill in the next one, and we'll come back and fill in your missing one as needed. Now I have to remember to hit reset. Then I'm going to take from 100, we're going to go up to 200 hertz. And in a moment, you're going to start counting, so be ready. Here we go. Choose your point that you're counting from, and 3, 2, 1, go. Halfway. And stop. All right, go back to the data table. Fill in the number of waves. I'm just going to fill in a fake number, but it's approximately what you should have counted. Maybe I counted 22 waves. Now check this out. Isn't 100 times 2, doesn't that make 200? And isn't 10 times 2 pretty close to 22? So that's something that we should see happening here, where the frequency is kind of matching the number of waves that come out. Let's go ahead and move on to our third one, 300 hertz. Okay, I've sped it up a little bit. The pitch would be rising. If I was playing the sound also, we'd hear the pitch going up. And we're getting ready to begin. So be ready to count on 3, 2, 1, go. Halfway there. And stop. Enter your data. Maybe I got like, again, I'm just making this number up. Maybe I got about 28. So record how many you counted. I'm going to reset this. I'm going to turn up the pitch, turn up the frequency. It's pulsing faster. The waves are also getting shorter. At the same time, the frequency gets bigger, the wavelength gets smaller. Here we go. On 3, 2, 1, go. Halfway. Stop. And record your data back here for the 400 hertz. How many waves did you count? Okay. Next one, 500 hertz. Hit reset. Start the countdown. 3, 2, 1, go. Halfway. Stop. Hey, incidentally, while you're writing down your data, we could actually be hearing this sound. I just didn't want to listen to it the whole time. But this would be making sound, and I think it would be hard for you to hear though, and it would be driving me crazy. So I did not turn the sound on this time, but if we were listening at the same time we were watching, we would hear the pitch rising higher and higher. So was that 500? Yeah. So we're halfway there. And as we continue doing this, I think you're going to see that you have to count faster and faster, which might make it a little trickier. So stay focused on this part. We're taking a little rest right now. Try to be as accurate as possible. Choose your one spot to count at. Maybe it's where they're coming out of the speaker. Maybe it's the speaker pulsing itself. Maybe it's where they hit the clock. I don't know. You decide where to count and stay focused for that little bit of time when we're counting. All right, let's go ahead and do our 600 hertz. Counting down, 3, 2, 1, go. Halfway. Stop. Please record your data while I set up for our next one. Hey, which do you think are going to be your most accurate measurements, when it was a low frequency or when it's a high frequency? What would you predict that you'd be more precise with your measurements?
Low frequency.
It's a little easier when it's slower, isn't it? Yeah, we got the fast ones to go still. So let's go ahead and do our 700. 3, 2, 1, go. Halfway. Stop. Record your data for 700. Come on back to do 800 hertz. And that means 800 vibrations per second. If this was going in real speed, this is dramatically slowed down, right? If this was going in real speed, the speaker would be vibrating 800 times every second. And that's one reason you got to be careful with not damaging your speakers when you turn up the volume too far. You can see how much the speaker moves. When it's not turned up very far, it doesn't move as much, which means it's less likely to get damaged compared to when it's turned all the way up. The speaker's really pumping. So that can tear your speaker apart. So be careful. Same thing can happen with your hearing too, where the really loud sounds can damage your hearing. Okay, so we're going to do 800 hertz in 3, 2, 1, go. Halfway. Stop. Record your data. So basically what happens inside your ears is that when these sound waves hit your eardrum, it causes your eardrum to also vibrate. And those vibrations actually start a fluid vibrating in your inner ear. And when this fluid vibrates back and forth, There are little hairs inside your inner ear, tiny little hairs, and some of them vibrate at one frequency and other hairs vibrate at another frequency. Each hair is connected to a nerve that takes a signal to your brain. When that hair vibrates, it sends the signal to your brain. And that's when you hear that particular pitch. So some hairs only vibrate at 900 hertz. Other hairs only vibrate at 200 hertz, like that. We can hear from 20 to 20,000 hertz. This simulation only goes up to 1,000, but we can hear all the way up to 20,000 hertz. Let's go ahead and do the 900. Get ready to count. 3, 2, 1, go. Stop. Now, one thing that can happen as we age, the little hairs that I was talking about that vibrate at specific frequencies, it seems that those hairs at the highest end, up in the 20,000 range, those hairs actually can get damaged. And so as people age, they tend to lose their hearing, especially of the higher pitched sounds. This can also happen if you've been exposed to very intense sound at any frequency. You can damage those hairs. So imagine if those little hairs are damaged at 900 hertz, you wouldn't be able to hear that pitch very well. And this can happen if you have speakers turned up too loud and you're too close to them. It can happen if you work in an airport, for instance. What if you're one of the luggage handlers that's loading and unloading luggage, and there's all these sounds from jets around you all the time? Next time you go on a flight, check those guys out. They almost always have headphones on, and they're not listening to music. They're just protecting their hearing from the sound of the jet engine. The same thing might be true of somebody that works with a jackhammer in construction. Or, for instance, my wife is a dental hygienist, and I think there might be some damage to her hearing in the high frequencies due to the pitch of the ultrasonic cleaning tool. So you want to be careful when you have loud sound around you, and I think that might be especially true if you're wearing headphones or if you have earbuds in. If it's pumping really hard like this, then that's going to pump really hard against your eardrum, and that's going to vibrate the heck out of those little hairs inside your ears, and that can damage your hearing forever. Once they're damaged, they don't grow back. So be careful. All right, our last one, 1,000 hertz, 1,000 vibrations per second. Here we go. Ready to count in 3, 2, 1, go. Halfway. And stop. Darn, I never hit 0.1000. Yesterday, I did like 3 or 4 times. I got it exactly at that correct moment. But that's okay. It's accurate enough for us. Okay, so at this point, you should have filled in this entire chart here. If you need to redo one of these, send me a comment so I can see that you need to have it redone, all right? And let me know. But I'm not going to redo it right away. Instead, we're going to figure this out, okay? So, calculated hertz. Hertz is the vibrations per second, okay? I'm going to write that up here. Hz, which is our symbol for hertz, named after the scientist who first described this, is vibrations per second. Okay? So when we set up the simulation, that speaker should have been vibrating exactly 100 times per second, except they showed it to us in slow motion. Okay? But because it was slow motion, we weren't going to count for a whole second. We only counted for 1/10 of a second. Now, if you take 1/10 of a second times 10, that equals 1 second, right? So you're going to take whatever number you had here, the data that you had, multiply it by 10 to fill in the calculated hertz. So for my first example, 10 times 10 equals 100. 22 times 10 equals 220. 28 times 10 equals 280. So you can use a calculator for this, or anytime you multiply by 10, all you have to do is take that number and throw a 0 at the end of it. So that would be the quick way to fill in this table. So I'm going to give you a minute to work on that. And now is the time to tell me if you need me to redo anything. All right. So while most people are working on this, maybe you need me to redo a particular value. Tell me how many hertz you need me to redo if you're missing something. Otherwise, just go ahead and fill in this row. And then give me a thumbs up when you're done with that row. Thanks, Andres. Good job, you guys. All right, way to go, Armando. Pretty simple, just multiply by 10 to get how many hertz we calculated. We didn't actually count 100 of them. We counted 10 and multiplied by 10 to get this calculation of 100. All right, good job, you guys. Way to stay on it. It looks like nobody needs me to repeat anything. Let me know if you do. We still have an opportunity for you to do that. Okay, our next column is finding the measurement error. In other words, how accurate were you? How close were you to the actual number of hertz? Well, remember, this frequency up here, I should have actually said that this was frequency measured in hertz, and that's how we show this. These are the actual hertz. How close were your calculations to that? Well, it's pretty simple. You just subtract. So I'm going to go 100 minus 100 equals 0. That was perfect. Let's see, what are we going to do? Subtract your calculated from the frequency. So for this one, it's going to be 220 minus 200 equals, my answer is 20. Whoops. Okay, so all you have to write down, of course, would be the 20. I'm just showing you how to get that answer. So I was 20 off, right? Now, this next one, I want you to look at this one in particular. Some of your answers are going to be positive and some are going to be negative. This one, I have to go 280 minus 300 equals my answer, which is going to be negative 20. Keep that negative sign there. Basically, the positive and negative numbers tell you if you overestimated or underestimated. So anytime you underestimated, you're gonna have, oh, I did it backwards, I'm sorry. I did both of these backwards. It should be the correct frequency minus yours. This should be a negative 20. This one I have to switch around to be 300 minus 280. This one's a positive 20. Sorry about that. So put this number in first into your calculator or into your head, and then subtract your calculated hertz from it. 300 minus 280, right? That's going to give you 20. Now, if it's a positive number, that's going to tell me that I underestimated. In other words, I was, the actual frequency was more than what I measured. I underestimated it. If it's a negative number, that means I overestimated it. The frequency was below my measurement, so it was negative. All right, go ahead and fill in all your measurement errors by subtracting frequency minus whatever your calculated hertz was, and then include whether it was a positive or negative answer. Give me a thumbs up when you're done with that. Let me know if you're unclear on how to do something. All right, thanks, Gus. Good job, Quetzale. Remember, if the actual frequency is less than your calculation, it should have a negative sign. All right, some more of you guys getting done. Thank you for letting me know where you are. Let's have one more minute to finish that up. we're almost done. We're going to complete this chart today. We're going to start number 1 down here together. And then I'm going to ask you to do a couple other things with the remaining time in class. And if you fall behind, you might have to consider that as homework. All right, you guys, so if you're still doing that subtraction, I'm going to ask you to stop for a minute and go back to it when I turn you loose, because I want to show you how to calculate the percent error right here. So how close or how far were we from the actual number of hertz? Okay, now this one, it should be kind of obvious. If you were right on, if you had it exactly right, your percent error is just going to be 0%. You don't even need to do the math, huh? But these ones we have to calculate. So here's how you're going to do that. You're going to take, probably at this point, you're going to want to get a calculator running, right? So to find percent, probably do want a calculator. And what you're going to do is you're going to take whatever number you came up with here, like this one was negative 20. There's 20, and I can make that a negative number right here just by finding this plus minus sign. I turn that to a negative, negative 20. I put this number in, I hit divide, then I put in the frequency, 200. Then I click equals. But that's not a percentage yet. To change this to a percentage, I have to multiply by 100. Just like there's 100 cents in a dollar, percent means it's out of 100. Now there's my answer. I was negative 10%. In other words, I overestimated by 10%. The actual answer was 10% less than my measurement. So I was off by 10%. Let's do that again for this one. I'm going to actually write it out here. So I'm going to take 20 divided by 300, right? Here's my 20. Here's my 300 at the top. 20 divided by 300 equals, let's see what that equals. Got to clear everything first. 20 divided by 300 equals 0.066667, but to make it a percent, I have to multiply by 100 at the end. I hit equals, I get let's call it 6.7%. Oops, sorry about that. Forgot to do something here. 20 over 300 equals 0.6 forever. But I'm going to multiply that by 100, and that gives me a final answer of 6.7%. Okay, so that's what's going to go down here, 6.7%. Keep track of your positive and negative signs, and go ahead and fill in the rest of that row. Please ask if you need help figuring out how to do it, and give me a thumbs up when you're done. while we're working on that, this is also the chance to see if you were more accurate at the low frequencies than the high frequencies. Remember, I asked you to predict which one you thought you'd do better on. Now we're actually going to be able to tell by comparing your answers at the low frequencies, your percent errors, to your percent errors at the high frequencies. We can tell. Thanks, Katsali. So the great thing about comparing the percent error is that it accounts for the difference in what we started with. So for example, for both my made up data for the 200 and 300, they were both 20 off, weren't they? They were both 20 away from the correct answer. But if you look at the percent, that 20 is 10% off for the 200, but the 20 for the 300 is only 6.7% off. This mistake of 20 off was actually less of a mistake than this 20 off because this had so many more. 20 off out of 1,000 is not very much, is it? Again, if you compare this to money, it starts to make more sense. Let's say you were 20 off of 100. Let's say you needed $100 to buy something, but you were 20 off. You needed 20 more, right? That's a pretty decent chunk. But if you needed to buy something for $1,000 and you were only $20 off, you're really close to being there, aren't you? So that same error is not necessarily the same amount of a mistake. Once you convert it to a percentage, you can really see how much of a mistake it truly was. Ideally, we'd like to be within 10%. Anything more than 10%, then you're starting to get a pretty big mistake. Anything less than 10%, that's okay, we can live with that. All right, and it looks like a lot of people are getting about done with this. That's good. And we're going to move on to the analysis. So once again, stay with me. Even if you didn't quite finish the data table yet, you can go back and fill that in a minute. And if you get lost on something, stick around when we end the meeting and I'll help you, or send me a note on Teams or an email. So question number 1 also starts with a math question. Find your average percent error. So now you're going to add up all your percentages here, whatever they might be, and divide by however many there are. I think there's 10. So you're going to divide by 10. I'm just going to show you what my average would be, but I only have 3, so I'm going to do it a little different than you. So first of all, I have to clear my calculator. I have to include the 0. So I add that in there. Then I'm going to use, if you know math, I'm going to use the absolute value of this -10. I'm just going to ignore the negative sign and I'm going to put 10 in there. Otherwise, the negatives and positives would cancel each other out, and that would not really be a very accurate way to find out what our overall error was. What was our average amount of error? Doesn't matter if it's an underestimate or an overestimate. Doesn't matter if it's positive or negative, it just matters how much the error was. So I use the absolute value. 0 plus 10 plus 6.7. You're going to keep adding and adding and adding, aren't you? For 10 different numbers. And then you divide by 10. For me, I only had 3 numbers, so I divide by 3. My average percent error was 5.6 for me. Now, like I said, if we end up with an average of less than 10%, that's reasonable. Okay? Notice that this question has 2 parts. First, you find your average percent error, then you respond to that. What do you think about that? Okay. Question 2, compare your percent errors for low versus high frequency. I would look at the first 3, maybe 4 Ignore the ones in the middle. So maybe compare the first three, 100, 200, 300, compare those percentages to the last three. How did the high and low frequency errors compare? Were you more accurate down here, less accurate down here, or were they about the same? And then give some possible reasons. Please be careful. Sometimes these questions have more than one part. You need to answer all the parts of the question to get full credit, right? Then you write a summary. So all this stuff you're going to do on your own with the rest of class, or maybe it becomes homework. And if you really want to stay on top of things, I'm going to ask you to do a little bit more than that today too. Not page 14, because this is our next lab that we'll do on Friday. So skip over page 14, but page 15 has summary questions. And I think you should be able to answer the first 5 questions at this point in time. Okay, there's a total of 8, but if you answer the first 5 today, or you have them answered before I see you again on Friday, you'll be in really good shape. And you'll have no problem finishing this entire thing on time. Okay? So that's all I have for you today. So basically, as a review, I wanted you to finish page 13, and I wanted you to do the first 5 questions on page 15. All right. If you have any questions, stick around. If you needed something repeated on the simulation itself, if you need to recount some of those, let me know, stick around. Otherwise, you can check out now and go work on your own, all right? So nice to see you guys participate. Let me know if you need any help with anything, turn in late work, and have a great day, okay?
You too, Fairly.
Thanks, David.
Thanks,
See ya.
Fairly.
All right, guys, see ya.
Thanks, Fairly.
Adios, you guys. Auf Wiedersehen. Bon voyage.
Thanks, Fairly.
See ya.
Thanks,
Thanks. All right, good job.
Fairly had a question. I just
Sure.
wanted to say that I turned in some stuff, some late stuff,
When did you turn it in?
last night.
Last night. Okay, I haven't looked yet today. So
Okay,
I want to
just letting you know.
congratulate you for turning in work. Good job, Kaylee. Keep it coming.
I was gonna ask you if I should put those in the notebook.
Everything should go in the notebook? Yes.
Sure. Okay.
Yeah.
Okay, bye, Fairly.
See ya.